Okay, welcome back from the break. Our next invited guest speaker is Professor Sumit Roy, who's from Fundamentals of Networking Lab, Department of Electrical and Computer Engineering, University of Washington, Seattle. Here's a little bio of Professor Roy. He received a Bachelor of Technology degree from Indian Institute of Technology in 1983, and MS and PhD degrees from University of California, Santa Barbara, all in electrical and computer engineering. His previous academic appointments were at the Moore School of Electrical Engineering, the University of Pennsylvania, and the University of Texas, San Antonio. He continues to be professionally active in IEEE communication societies, notably IEEE Future Networks Initiatives, for which he currently serves as distinguished lecturer. He has served as associate editor for all the major ComSoc publications, selected areas of communications, IEEE translation of wireless communications, IEEE translation of mobile computing at various times, and was previously selected for 2 stints as IEEE ComSoc distinguished lecturer. He was also elected to executive communication member for the National Spectrum Consortium, and between 2020 and 2022, he served as the program lead for Innovative Beyond 5G program within U.S. Department of Defense Office of Undersecretary. Research and Engineering 5G to SG initiative. It's a great pleasure for me to actually introduce Professor Sumit Roy. Professor Roy, the floor is yours.
Great, thank you. Let me confirm, can you hear me?
Yes,
okay.
I can hear you.
All right. And can you see my slides?
Not yet.
Okay, let me share my screen. How about now?
Yes,
okay.
Yeah, we can see now.
Very good.
Can you
Thanks.
go to slideshow? Okay, yeah, we're good. We're good. Thank you.
Thank you. First, my sincere appreciations to the ACM Baltimore chapter chairs and to Ashutosh for the invitation. Apologies, I couldn't be there in person. I hope to make this up on a future, hopefully recent future, DC trip sometime. Visit APL, always good. So today, what I'm going to talk about is on automotive radar. And as befits an ACM audience, I'll try to focus on 2 aspects, sort of half and half. Firstly, to look at the operations of automotive radars as a network. And then, as you can expect, and I assume this would interest a cross-section of people, to look at how radar vision can contribute to this rapidly oncoming future of autonomous vehicles. So the premise of what I'm going to say is based on something we all know, which is the integration of sensors. Broadly cameras and radars, of course. LiDARs are the rich man's version of, or the more expensive version of sensors like radars. But increasingly, there's a consensus, and which is proven by industry adoption, of more lower cost radars that operate in the millimeter wave range, for various applications. These are clubbed under, either vehicular safety or what's called ADAS, Advanced Driver Assisted Systems, that allow for things like collision avoidance and lane changes and obstacle detection avoidance, etc. Right? All in support of sort of future autonomous, vehicle operations. Okay, so what I was going to do was, before I sort of give you the outline of my talk, mention that there's an excellent evaluation board, which much of the work that you will see in my lab is based on. So this is a chipset. Here's a picture of the AWR series from Texas Instruments. There's a motherboard and a daughter board, which essentially implements a radar transceiver, TXRX. And it operates in the, nominally in the 77 to 81 gigahertz, band that is allocated for radar, in a millimeter wave radar. And actually it can support, MIMO radar transmission and uses an ARM processor. So we have these boards in our lab. And as you will see, we have put this to interesting use. So um, uh, before I go further, as you well know, most of the sort of low-cost radars, the kind of radars that historically have been designed, are use what's called FM frequency modulated CW or SWEPT, or a chirp signal. And typically here some numbers on the left-hand side as to what the chirp is, a linear frequency sweep, characterized by the slope, and the slope here is like 21 megahertz per every microsecond. And the number, usually for radar signal processing, you collect a number of chirps, which constitute a frame, which is typically called a coherent processing interval. But at any rate, the function of radar is, of course, as a sensor, and it is to firstly determine if a target is present, right, based on backscatter, right, and further, after detection, you would want to know something about the target. Notably, radar is synonymous with ranging, i.e., finding relative distance, to the target, as well as other parameters like velocity. Okay? Now, the key issue is, of course, that as radars become commodified, and all vehicles have radars, the design of radars, the typical radar that you and I see is when we go to the airport, or in the evening news when they talk about sort of weather radars, right? And these are standalone, radars that are intended to identify, targets, single or multiple targets, but in allocated spectrum without interference. However, as in this mock-up scenario, right? If radars in vehicles, FMCW radars in vehicles become commodified, what you have is what we call a radar network scenario, or a radar multiple access scenario, where if you look at the car vehicle to the left, which is sort of the reference vehicle with its radar and is trying to identify the target in yellow, a pedestrian crossing, right? It must do its job, i.e. detect the presence of the target and determine range and velocity and any other parameters or the characteristics of the target in the presence of other radars which are also chirping. So the other radars which are also transmitting simultaneously in the same frequency band constitute that strong interference signal. And so it leads to this multiple access problem, which is very similar to what we do in communications. The point is that currently, this thought process of looking ahead to the future in which radar operations become quote unquote congested because of this multiple radar or coexistence problem is not on anybody's horizon, because we continue to try to design radars as if the operation was interference free. Okay, and this is one of these interesting issues that the radar has to be integrated into a vehicle. So it's the vehicle owner who must see a value in actually solving this problem. But as you can imagine, simple scenarios, you're in a, in a city at, commute during morning or evening rush hours, and your vehicle is surrounded by a large number of other vehicles. Each of them, or many of them, now have are by commodification have radars. All of them are now transmitting simultaneously, and so therefore the ability of any one vehicle to get accurate target detection, or in general get a mapping of the scene. So as you well know, from individual targets, the bigger objective, or the more broader objective of using radars is to essentially do a full scene representation. Is to understand the environment by using radar imaging or radar vision, as we'll talk about later, it will be impaired because of the presence of other radar. So by and large, this is one of those future-looking problems where one can take the learnings from design of multiple access of radios, of communication radios, and use that knowledge to try to forestall or solve a multi-radar coexistence problem. Okay, so that's the first part of the talk, and then the second part, time permitting, I'll talk about using the same infrastructure that you saw, the radar evaluation board, to actually advance the state of art of radar vision. And as you can guess, it is to essentially radar sensing is a detection estimation problem fundamentally in the presence of a lot of such increasing amount of interference, and with a very large number of targets in the vicinity where you're trying to do scene reconstruction. One is naturally drawn towards neural nets, employing deep learning type approaches for improving the target recognition performance, and we'll talk a little bit about it. So, all right. So moving on to the first problem. So one very simple way. So what I will try to do is, at some point, I will again provide references to some of our papers. I'm happy to follow up with anybody now at the end with Q&A or later if people have specific questions. But what I will try to do is I will try to give you sort of an intuitive sense, without going into the details of the result. And I hope, those particularly who are network engineers will see the analogy. So I'll try to draw analogy from the experiences of multiple access design in networking, and apply and show how the analogies may actually provide insights for this mutual radar interference problem. And so one way to construct a design. So I've just said that radar performance, traditional radar performance, where the radar is detecting a target and estimating its parameters, is going to be impaired because of the presence of multiple other radars in the vicinity, which are co-located and using the same frequency and time resources, right? So it's overlapping in frequency, time, and in space. And so this leads us to what traditional network engineers call a multiple access problem or a scheduling problem. And one way to construct a version of that scheduling problem is if you imagine a highway, a linear highway, okay, with the cars arrayed as shown. Here's a question. We can try to define the notion, and each of these cars. So whenever you see a vehicle in this mock-up, imagine each of these vehicle as a single radar. So in fact, as I have indicated, vehicles in reality will have multiple radars, front-looking radars and back radars, side radars. But just to make things simple, let's assume vehicles have a single radar. Okay, and the point is, we can identify or we can construct a simple notion of capacity by asking the following question: that in this linear topology, right, where these cars may be randomly placed, what is the maximum number of non-colliding transmissions that one can design for such a simple network, right? Okay, for a given time frequency resources. So as we know that radars consume, they send chirps, which is a linearly swept, frequency signal, okay, where you can start from a minimum frequency, go to a maximum frequency, and the frequency changes linearly over time. So it uses this, an amount of time frequency resources. So given that you have the entire system is allocated a certain amount of time and frequency resources, what's the maximum number of non-colliding transmissions one can pack in? And by non-collision, we will quantify it, as we'll see later. It essentially indicates the sort of orthogonal multiple access schemes that we can design. All right, so let's look at this a little bit further. Okay. I think I can skip this and then go to some details about. So in order to try to get to the bottom of this problem, one really needs to kind of understand how radar signal processing works, right? And so here in this slide, I've tried to capture this, and I will, again, I try to keep this intuitive. So firstly, I said these are all FMCW, frequency modulated continuous wave chirp radars. On the top right, you can see frequency versus time, and that's a linear slope, right? In the time, sort of in the signal or amplitude versus time, here's what the waveform looks like on the panel, right? Right-hand panel below. All right. Now, the left is a typical system operation of how detection of a target. So on the the target is shown as a black hexagon, right? In the middle is the reference vehicle with the radar, right? So there's an antenna sending out that FMCW signal, and there's the blue arrows represent the emission from the radar, which is then backscattered back to the antenna, right? And then goes through the duplexer, into the mixer. And the lower part is the processing chain, right? And keeping things at a sort of a sufficiently simple level, the processing after filtering the output of the mixer essentially identifies, the presence of the target, and the presence of the target is represented by what you see as the echo, right? So the blue arrow and the delay of the blue arrow with reference to time t equals to 0, okay, will provide a notion of range, and you will see this in a subsequent slide, right? Okay, and you will see that with demodulation of a chirp, the difference in frequencies, okay, actually translates, because there's a linear relationship between frequency and time. It maps to a difference in time, which is effectively range. All right. So the point is this: if there was a single target, you would just see a single echo. Now, unfortunately, because of the presence of an interfering source, another radar, another car with another radar mounted on it, right? And that is the antenna who's outputting, this another interfering a similar FMW signal, right? FMCW signal in red, you get a ghost. So a ghost, by definition, is a false target, right? It's simply another source which is masquerading as a backscatter from a real target. And the presence of interference literally leads to what you call, false targets or false alarms, right? The radar, this transceiver, is designed fundamentally to actually detect whether the blue target, or the blue return from the target is there or not, right? So as what is not shown here is, of course, there is a target detection problem. Now let me move to the next slide to sort of further explore this. So if you in this slide, what we are showing is the magnitude of the return from various sources, the target and the interference versus range. So one of the things that you notice typically is that when you have multiple targets or a target and an interferer, hopefully they can be discerned or distinguished by the fact that there are different ranges, right? So let's take a case like here that the target is at a particular range, and this is shown by the blue peak. So what you have for the target is that I'm sorry, the target is identified by the red or curve, right, which is where the target is at a range of, say, 70 meters or so, right? And the interference is one of these other curves that you see. If the so this slide sort of shows several facts. First of all, typically a target and an interferer, hopefully I should say, is at different ranges. So the echo from the target and the interfering signal after it goes through the radar processor will occur at different ranges, right? And so that's what's shown here. Okay. However, what's further shown is the following. I said both of them are these FMCW signals. They are they are demodulated by the radar receiver chain. And here, if both so there are two parameters here. You'll see alpha. Alpha is the chirp slope, okay, and alpha tilde is similarly. So alpha is the slope for the reference signal, for the target, for the the emission of the reference radar, and why alpha tilde is the slope for the interfering radar. Now, you could argue that, if these are all standardized, you would expect alpha tilde and alpha maybe to be very close to each other. But, there may be manufacturing tolerances, etc., or, there may be different manufacturers who choose different slopes for whatever reason. So we've used some examples, which includes the fact that alpha tilde and alpha may be equal. Yeah, so the ratio is equal to 1 or maybe unequal, smaller and larger, etc. To actually highlight, what happens, to the receive chain, in the reference radar. So if alpha tilde and alpha are the same, which is equal to 1, what you see is that the interfering target appears like a pure echo, right? So it's a strong echo signal. And what the thing that you notice is that the target is actually weaker. Okay, so the receive power, the magnitude is weaker than the interference. Now, this is again very typical because, as you know, the target return is a two-way, is a backscatter, whereas the interference is a one-way, right? And so, as you well know, by normal propagation mechanisms, in scenarios, typically the reference signal from the desired target is going to be weaker than the interference. Now, what is interesting is that when the two chirp slopes are not the same, the interferer does not look like a ghost target, okay, but it has another deleterious effect, which is if you now look at, say, the green curves or the magenta curves, right, or the yellow curves here, which is how the interferer, okay, looks at the output of the reference, receiver, radar receiver, you can see it looks like broadband noise. Okay, but again, depending, typically the broadband noise actually exceeds the target peak. So the point is this, that this is for signal processing engineers not too hard to understand. It has to do with the coherence or the lack of coherence between a source and the desired source and an interfering source. So when there is lack of coherence, the lambda tilde is not equal to lambda. The interferer appears more noise-like, broadband noise-like, but the noise can often hide the signal. By and large, the point is this, that when you're in this congested multi-radar scenario, target detection, detection of the desired target by the reference radar can be seriously compromised, and that's a problem that needs attention. And the way to attack to address this problem is to is to try to employ notions of multiple access that we have done in networking. One way to do it. Of course, other ways to do it is to improve, so it's a combination of things to solve this problem. One way is to schedule transmissions and or multiple access, and the other way is, of course, to improve the core function, which is radar detection and estimation. Right? So I just wanted to sort of give you a sense of what the a radar, for those of you who haven't seen, what target and interference or ghosts look like, right? So a typical radar processor. So what I have done is I've sort of detailed out post ADC. So I mentioned to you that the target, the sum of the target return in blue and the interference is mixed, goes through a low pass filter, right? And after that is ADC, and then you have this digital or baseband processor, right? Typically, again, for these chirp signals, what we do is we do these FFTs or DFTs, right? And we do two successive FFTs or DFTs, one for the range, one for the velocity, and then look at the output of these two DFTs to actually implement the detection algorithm. And the output of the detection algorithm looks something like this in blue, or in this purple panel, right? Where you have a ghost here, okay, and a target there. And the difference between the two, this is a simulation, of course, clearly. The difference between the two is that we pick the target and ghost at, both different ranges. and of course at different speeds. Of course, this is by on purpose in this sort of congested parking lot or evening commute scenario where it's an effective parking lot on the freeways. The reference radar, the target, and the interferers may not be distinguishable in speed, because both of you are essentially static, right? And they will be in close proximity, so again they may not be distinguishable in range either. And these are challenging circumstances, right? So, okay. One of the things I also wanted to bring out is that in order to do velocity estimation, so you've seen that in the previous slide, the output of the radar is to do both range estimation and velocity estimation. One of the key ways in which, with FMCW modulation, one does velocity estimation is to actually send a succession of chirp signals. So you send a frame. A frame includes L chirp cycle. So it's a cycle of L chirps sent back to back, and the assumption is that during this sequence of L chirps, it's called a coherent processing interval, i.e., the phase and frequency relationships during this duration. So each chirp, you can think of it as a few microseconds. So if L is like 100, the duration of a frame is maybe 100 microseconds or so. Typical numbers. That during this interval of the processing can be coherent. Okay. All right. As I already mentioned, that you do this 2D processing, and so the point is, radar pictures looks like 2D range velocity matrices, right? And depending on the number of quote unquote targets, now I'll use the generic term targets, which includes desired as well as false or undesired, right? You will have a certain subset of these these matrix elements, right, lit up, right? And the point is this, that if there was only one permissible target, the blue, right, anything else is a ghost or a false target. Okay. And the issue is, can you determine so a priori you don't know what's the desired versus undesired. Remember, everything works perfectly if all you are expecting is a single target. Then you only expect one of these bins to light up, right? And you would declare that to be target presence. Of course, even with a single target, realize that you may sometimes miss a target, right? But the greater issue occurs that when you're designed to just in this matrix just have one bin, your expectation was one bin to be lit up at most, right? If you have multiple bins lit up, now you have a problem of identifying which one of them, if any, is the true target, and the rest are false. All right. Okay. So this is how I just wanted for those who haven't looked at doing a simulation, this is how a radar image sort of looks like, right? And on the right hand side is the I represent the power at the output. All right. Now, so let's go to the the potential sort of solution methodology that I indicated, which is about design of multiple axes, right? So let's try to bring the knowledge of networking into this domain, as I kind of indicated. So let's say you have this system bandwidth given. I indicated that radars are allocated 77 to 81 gigahertz, so 4 gigahertz. What you can do is this, so whatever I mentioned with the current hardware is that the radars occupy the full 4 gigahertz band, right? Well, one thing we can do is, of course, you can do sort of, in the interest of orthogonal frequency division multiplexing, you can actually divide this 4 gigahertz, the total RF band, into subbands, right? And then allocate radars, to different subbands, right? So here, the assumption, so the first, the system that we'll talk about is, so again, everything that I talk about, you can just imagine a very simple, network model of, a linear, vehicle, a linear road with vehicles, randomly placed. You can, the analysis that I will do says, okay, these are, each vehicle has a radar, right? And that's the reference radar. It's transmitting to, identify targets in the vicinity, but everybody else is doing the same thing. So the rest are all interfering radars. And what we'll do is we'll have this, well-known sort of analytical model where, I draw a circle around the victim radar, and you can call this a disk interference model. You can claim that, any radars which are within the disk will contribute interference, into the victim radar's, receive chain, right? And the ones outside won't, right? So based on this simple model, and as always, you can do better than this model, but the point is this model suffices to highlight the kind of multiple access ideas that I'm going to, propose. So first of all, what are kind of multiple access ideas? So I'll pick one, which is really, like unslotted aloha. For those of you, remember, basic networking course long ago, right? This is not a surprise, right? And this applying unslotted aloha, right, to this sort of random frequency division multiplexing scenario. So first of all, the RFDM, or random frequency division multiplexing, really is take the full band, 4 gigahertz, divide it into M subbands. So, if M is 4, okay, each now radar only uses 1 gigahertz modulated bandwidth, right? Not all 4. Okay, so there's a cost to there. It's not a free lunch, so we can talk about this later. Okay, each radar, say resolution takes a hit. Anyway, so, but in terms of multiple access, what you can now say is this, that each radar sort of randomly picks, firstly a transmit time, right? Okay, and you can see that, and then, picks a subband, right? So now, as this is an example, if you have 2 radars, a red and blue radar, right, their transmit times are offset because it's unslotted, right? So they are not, so which is appropriate. Remember, these are 2 radars on 2 different vehicles, and you have no expectations of, them being synchronous. Second, this is by purpose, this is a bad scenario where, the red and blue, the chirps, right? This is frequency versus time, right? They overlap substantially, okay, significantly, all right? And so you can expect that there's going to be, why? Because they both pick the same subband. Obviously, if one radar picked one subband and the other radar picked a different subband, they would be mutually non-interfering. But this is the the sort of the worst case here, right? The point is each radar picks one of these subbands and stays on that subband, right? For the duration of, say, L chirps, which is the coherent processing interval. Of course, this leads to why do you do this? You can do frequency hopping, and later on, I'll just mention that these are obvious improvements on this basic idea, and this basic idea is simply to level set, an initial concept for multiple access of radars. So the key thing is that suppose you do have this RFDM, random sort of initialization of radars, and now each of them picks, say, the same band. So here's what happens, right? I told you that the reference radar processes the return in range DFT, does 2 these DFTs. And there are 2 scenarios. And what I would like to summarize is this. Again, these are results from simulation, but from extensive simulations, and we can stand by this, that what happens is that if you have 2 radars, right? And so one is the desired to the reference radar, the target, and one is a ghost radar, right? Now, 2 things may happen, right? The target and ghost radar are in different range bins, or they are in the same range bin, right? And in both cases, as you can see, from looking at the power. So if you look at the mid slides in both, that's the kind of the full picture. It is the z-axis is the power versus velocity and range, right? So you did these 2 DFTs, and then you measure the power in each of those bins that I showed before, right? And what you see is the following. In both cases, the target gets hidden, all right? So as I indicated to you, that whenever the target and the ghost, right, or the false target, are close enough to each other, either in range or in velocity, right? Okay, with very high probability, you have a false alarm. A false alarm means that you cannot detect the desired target. You actually can see maybe the false target, and so. Given this, right, and I will, refer you. So I'm going to skip over. I'm not going to show any, analytical details that lead to these results, and I will just point you to some paper for those of you who are interested to follow through. What you can compute is that what is the probability of missing the target? So this is the target misdetection probability, right? This is the event E, MD is the misdetection, right? And there's on the right-hand side a formula, okay? And the formula has a lot of parameters. So first of all, one of the parameters is lambda, which is the mean vehicular density. Remember, vehicular density is the stand-in for number of radars. Each vehicle is a radar, for this, right? Okay. Then FH, is the bandwidth, of the system. H is the alpha that I had previously, which is the chirp slope, right? M is the number of subbands. Okay. Right. And Pn and X, right? Are quantities that describe. So for X is the number of desired targets. You can put this equal to 1 just for simplicity, right? So the reference radar is trying to detect maybe a single object, right? Okay, and Pn is the probability that this the desired radar and the ghost or the false radar or the false target, right, which is this interfering radar, are close enough to each other in either range or in frequency, which leads to misdetection, okay, or false alarm, right? So computing this target misdetection probability actually allows me to answer the question, what is the multiple access capacity, which is the average number of, orthogonal transmissions, right? That one can pack into such a system, and that's the answer, below. So the key thing is this. If you look at this formula, so this C is for capacity, right? The sort of the number of maximal such transmissions that you can pack in, right? Such that each of them, what's a capacity, all of these are successful, right? Okay. It's, on the right-hand side, it's a function of lambda, but then it is killed exponentially. So if you look at the dependence on lambda, it rises with lambda, but then it is killed by the exponent of -2 lambda, and then there's some constants with it, right? And if you recall this, and I can show you on the next page, this function, if it's plotted as a function of lambda, is something that we have seen before. It very much looks like sort of the multiple access capacity of the family of Aloha or slotted Aloha, right? As however, if you okay, so this curve has, this plot has multiple curves. The equation that I just showed you before actually, is the curve at the very bottom, right? So it's actually this horizontal curve, the UA RFDM, largely because of scale, right? The point is this: you well know that with this sort of multiple accessing, you don't expect very good capacity, right? Okay, it's really very low. The rest of the curves I will talk about very quickly. Okay, where these come from, and these come from more enhanced ideas for designing radar multiple access. And the first is to add frequency hopping. All right. So with frequency hopping, here's the example. Previously, you recall that with just slotted Aloha, each radar simply had a random start time, but then it stayed on the subband that it picked, for the duration of a coherent processing interval. Here, in each chirp cycle, the radar reselects which subband that it picks, right? So as a result, even if, let's say, you start with the first cycle and the red and the blue overlap, then for the next chirp cycle, right, the red may randomly pick a different subband from the blue, etc., etc. Okay, so therefore, the ability to be non-interfering is because of this random choice is inherently greater, right? And then we can see that it'll show up in the capacity equation. And one of the things is that as long as the desired target, right, appears coherent, right, and the host, what will happen is this. So you can see the ability of the radar chain to actually detect your desired target while the interference may be hopping over is actually enhanced. Okay, So, as compared to the picture I showed before, when the target and ghost fall into different range bins, right? Whereas in the, the standard slotted Aloha scheme, you would still get false alarm. Here, this is the left-hand side. These are resolved, right? That there is no false alarm. However, you don't resolve all the false alarm or misdetections on the right-hand side when you still have the difficult challenge that the ghost and target are in the same range bin. You may actually not see the target. Okay, so you solve some of the problems, you don't solve all of the problems. Right? And then, you can again look at our paper and see how with frequency hopping, there's an additional gain due to frequency hopping, which in turn leads to enhanced multiple access capacity, which is, if I just allow me to go back, which are these curves now? So if you look at the curves that are plotted in, let's say, the green curve or, the yellow or the purple, these are different, these are capacity of frequency hopping for different parameters, right? And they clearly exceed the rather poor performance of the basic slotted Aloha. Okay? So again, I'm just appealing to sort of intuition without going into specific details, but I think happy to clarify further as needed. And then similarly, why stop at frequency hopping, right? Frequency hopping is a sort of a code in the frequency domain. You can do phase coding as well, right? So the point is this, that in the transmit chirps, right? You can put additional phase modulation, right? So you can put a phase encoding, and here it shows that before all the chirps started off with, let's say, initial phase 0, but you can randomize that, and you can actually put a phase pi randomly. You can pick 2 phases, right? 0 and pi, and then randomly pick a phase on each chirp cycle, right? And that also has some benefits due to phase coding gate. By and large, the whole point is this, and the result from phase coding is shown in red. Again, initially the capacity improves, it hits a peak, and then it exponentially gets killed off. But the benefits from frequency and phase coding are obvious relative to the pure random access. So hopefully this gives you an idea that this what do we an oncoming problem of congestion in the radar band, right? How we may actually apply traditional multiple access techniques to radar for radar to enhance radar coexistence, right? And here's a chart that kind of summarizes. Okay, now pivoting, these are the references. I will share this slide, and you're happy to look further. Pivoting to the next topic, I'm going to talk about what the application of the system that we have to actually enhancing target detection and object recognition. As I said, that you could approach this 2 ways. One is to, of course, design better multiple access or scheduling for the participating radars who are mutually interfering, or you can look at improved target recognition. And I'm going to skip all this. This is pretty sort of known and similar. This is FMCW. The point that I wanted to make is that the reason that FMCW radars are kind of commoditized de rigueur on these vehicles is that they are indeed a lower cost substitute for LiDARs, right? One, but they retain the ability, and this is the key point, right? That first of all, they are very robust to environmental conditions. Much more so. So we all know, we have all used cameras, and that your camera picture is greatly challenged when there is low light or other environmental events like fog and so on and so forth, right? Impairs the camera image, right? And so the radars are a great sensory complement, to the optical sensor, like a camera, right? Further, they are very sensitive to velocity changes in object movement, right? And inherently, so therefore, they are great, in discriminating objects on the basis of speed, static from mobile objects. The major, cons of a radar is that while it's, provides, depending on the bandwidth used, great range resolution and very good Doppler, resolution, it has typically poor angular resolution. But this is one of the areas that new hardware, is addressing by incorporating, concepts like, MIMO, applied to radar, as well as, the ability to coherently process through, notions like synthetic aperture, so therefore you get much, a bigger radar aperture in angle, right? And improve the current, insufficient angular resolution. So as you know, angular resolution is important. If you think about a forward-looking radar, you do want the radar beam in order to not just do sort of same lane, sort of front, bumper type collision avoidance. You also want, if you changing lanes, to be able to cover a certain azimuth angle, right? So lane change. And also, if these radars were mounted on vehicles, avoidance of obstacles like bridges or overpasses, or if these are mounted on things like UAVs, the ability to have angular resolution would be very important. So anyway, so these are all sort of issues, some of the pros and cons. One of the other cons is, of course, that unlike optical images, right, which are easily interpretable, radar images are much more difficult, right, to interpret. So therefore, perception, abstracting, targets, etc., has requires much greater effort. Okay, all right. So this is the okay. So again, just wanted to show you this, what we have done with the TI hardware that we have. You can go out, near campus and parking lots and get actual. So we wanted to show you that you take a camera image that's on top, and if you can see there's a person standing in a parking lot and in a background, and then you can process the same image using a radar returns, and here's what you would see, right? Okay, so we've gone around taking a whole bunch of images of both static objects with the and I will show you, with a camera and a radar mounted on a vehicle. Okay, and the point is this, right? We do believe that this combination, in the sense of sensor fusion of both the camera, the returns from the camera, right, and what you can glean from the camera, and what you can glean from the radar returns, are sort of a very good, a very good compatible or complementary, sensory sources. They tell you different things, and more importantly, they complement each other in the regimes in which they are effective. So as you know, on a nice bright day, if you have a large number of camera images, you can use this to train neural nets, like has been done before, right? I mean, has been done now for a long time, and it's well known that deep learning, convolutional neural networks, CNN, employing deep learning algorithms, have done wonderfully well, right, for object detection, classification, etc., right? And there is this very well-known sort of benchmark, computer vision algorithm called YOLO, you only look once, which has provided sort of the benchmark for object recognition, as in this example, right? So the point is this, that we know already we have very sophisticated sort of tools from computer vision, or increasingly sophisticated tools from computer vision, which are very good at doing object recognition on camera images, right? And as I said, the presumption is that you have a large number of sort of training images taken in good scenarios. And I just said that the major value add of the radar is not that you necessarily need this for the scenarios in which the camera images already give you good scene understanding or perception. It's when the camera is ineffective, which is in poor lighting condition, or other environmental scenarios like snow, rain, fog, etc. That's when really the radar comes into play. Okay? So the idea is to combine the two, right? And the way that we are looking to combine the two is, let's say you have a scene, and then you observe that scene with both a camera and a radar, right? Because you collect this, suite of training images, and the idea is this: that if the scene is in broad, nice daylight, good, then we can use the sophisticated, scene understanding from camera, as I've just said, to actually train the radar. Okay, so one of the big benefits. So this is like cross-train. Use the camera to train the radar, such that if you went back to that same scenario, but in a very different environmental condition, nighttime, fog, etc., where only the radar is your sensor for navigation, then the radar, because it has been trained, with a camera, cross-trained with the camera set, is able to perform, well. Okay. Now, this has, as I said, significant benefits. First of all, it's if you were only to do this, with the radar image itself, it is hard to manually label the image. So as you know, you need, if this is trained, these DL algorithms, these are a large amount of training data, they have to be labeled, and that's hard to do, manually, particularly if you're looking at radar images, which I've shown you some examples before. Yeah. Whereas the camera image, we have already have these, the ability to label this is, much easier. Right? Okay. So what we have is this, that, I wanted to show you that we basically have mounted in a rigid chassis both a camera and a radar, and the radar is the radar that I show. Okay. And then what we do is we drive around, and we take, the images of the same scene with both the camera and the radar, right? And they are synchronized and calibrated, right? And then we use the camera to do the object detection, etc., and provide object class and location, and we use that as inputs, to the radar, right? And then into the radar, you provide in the testing stage totally different sort of images, right? And the radar is, tested on its ability to accurately, say, for example, detect objects and classify objects in those test set on its own. Okay, so this is our setup, right? So I mentioned to you that we have put together a platform, okay, and which we mount on a vehicle, and we drive around, and here we have a very large set of images that we have, right? And we partition this image. We take the good set, and we use the the camera to do object detection recognition, and then we extract the features when we use this to train the radar, right? Okay, so again, I wanted to now go back to some basic radar signal processing. Some of this you have already seen, right? Again, so post the mixing and low pass filtering after the ADC, right? We do some pre-processing, which I won't go into. But now I said traditionally, we do 2 FFTs, one for range, one for Doppler, right? Now I added a third, okay, which is for angle. And when I say angle, you can just imagine this for azimuth, for a not elevation, for a forward-looking radar. Okay? So as if we do 3 FFTs, so instead of a 2D map, as for 2, you get a 3D map, right? Range, velocity, and angle or azimuth, right? So we transform the return into a 3D data cube, right? For further processing. So anyway, so the point is this, that we are going to build, based on how the radar transceiver actually processes the signal, and then detects it, right? And then localizes it in range, velocity, and angle. We are going to, so I just wanted to say that. So we construct these 3D data cubes, and then we construct this over time, right? So we have, frames, multiple frames, right? So for each frame, we have a 3D data cube, right? And the reason to use, multiple frames is, of course, to capture the time. Evolution. So we also get the time varying or the temporal history of the target, right? So all of this leads to our architectural concept of what we call our new radar network architecture. So this is a radar net for vision, for radar vision, for scene understanding. All right. And here you can see from the left, we do this 3D FFT. And then we have this, the CNN, the convolutional neural network, the familiar autoencoder architecture, where we have actually 3 branches. You have a top, middle, and the lower branch. And what we do is this, and I'll explain to you the reason for this. So we take that 3D data cube and we actually slice it. We slice it in, range and angle, the top, okay, then range and, Doppler, D is velocity, Doppler, okay, the second, and then angle, velocity at the bottom, right? And then this passes through this, autoencoder, okay, and it extracts features, okay? It extracts features in each of these planes, and then the whole idea is this: the reason to do this in these 3 things is to then do a feature fusion module, right? And this, after we fuse the common features from these 3, sort of, okay. So the reason to do all this is, okay, this, okay, is sort of 3 perspectives which allow us to fuse the common features from these 3 perspectives, right? And okay, so let me just say what these are. I give you with an example. So just before that, just for dot the i's, the CNN that we use has 6 layers, right? Convolutional layers and 3 deconvolution layers. So here's, and these are the parameters of those layers. It's pretty standard. If anybody wants more details, happy to talk offline. So the reason to do all this is this fusion piece, right? And the intuition here is that, if you look at how we determine objects, right? I mean, the eye, which is a stand-in for the camera, has good range and angle information, right? Whereas, the radar, which is very good in doing range or distance, right, on velocity, gets us other information. So what we would like to do is that we would like to combine the information, this common information from all those perspectives, and actually, get a fused feature map, right? So this is the new sort of, fusing, this. So this feature fusion, I can talk offline. There's some details on how we do this, but essentially, what we have is this. This is sort of the final, radar, net. What you have is that you have this sort of input data. Let's say, one of the features is a range angle, and you get a heat map, right? And then, you have a center key point that represents an object. So an objects are simply sort of median locations, right? And what we do is the following: in each of these locations, which could be like a spike, we put a sort of a Gaussian distribution around the center. This is for training, and then we employ a loss function, right? Okay. So given the ground truth from the camera, we employ a loss function using that Gaussian kernel, right? And we do a few other things to minimize irrelevant learnings, okay. So such as preserve symmetry from flipping, from translating. These are all sort of known things. So I'm going to skip all this and then just quickly move over to showing you some results, right? So here's a set of pictures, right, of various targets: cyclists, pedestrian, cars, right? And in good daytime, right? Nice. And you get the image on top. You get the camera, I'm sorry, the camera image on top. You get a radar heat map, one of those 3 slices, say the range angle, right? As is appropriate here, okay? Not much of, okay. We are not using velocity here. We're just using range and angle to discriminate the objects in this image. And then you get this radar net result, right? As you see below, right? Using the method that I've shown. Now, the point is this, right? You apply this to, the same scenario on the left, daytime, and on the right, nighttime, right? Okay. And now, so the whole point is this, right? Having trained the radar, cross-trained the radar with the camera, input, via the radar net, right? One would like to see how the radar performs when all the test data that is given is like, for example, the nighttime. Okay? And here's some, usual ways that we determine, in this machine learning community.
Five more minutes. 5 more minutes, please.
Yes, I will, and actually I'm nearly at the end. So So, the traditional metrics here are, average precision and average recall, right? And precision is true positive over true positive, false positive, and recall is true positive over true positive and false negative. And I just wanted to show you that, if you look at the method that I just said based on this cross training, that's the last row, right? Relative to sort of the benchmarks in the literature, okay? And the benchmarks in the literature. So, for example, if you look at different scenarios, the parking lot scenario, the curbside scenario, or more, the most challenging scenario, of course, the on-road scenario, you can see the extent to which this cross-training actually, benefits, right? It improves, both the precision and the recall by several percentage points, right, overall. So having said this, right, I'm going to sort of, in the interest of time, again, happy to send you references. We have some estimates of the time complexity and the algorithmic complexity space that it requires, right? But I wanted to end by saying that, this is sort of a plug for this sort of sensor fusion, this cross training. And with that, I will end. There's some other work that I'm doing on MIMO SAR, but I'll leave that for some other time. Thank you. Happy to take any questions.
Any question from the audience here? You have a question? Yeah. Go ahead.
So I guess my question was, I'm not super well versed with physics and waveform structures. I actually come from a medical background, but my question was regarding the implementation of artifacts within our waveforms, using some kind of fragmented patterns or sequences to embed data and having that fragment or that pattern be recognized as a vehicle, for example, or a transmitter rather than actual signal itself. So you can have wave shifts at patterned frequencies. Do you think that that would carry any use, or is there a purpose or value in that technology?
Okay, so if I understand your question correctly, so I think you're talking about, the vehicle, when you say patterns, sending some kind of ID, right?
Right.
Right. So, so let me say this, right? So if you look at the radio analogy, correct? You look at Wi-Fi and so on and so forth, right? I mean, you have a BSS ID, when you go somewhere, you log on, there's a name for the network, right? It essentially is a network ID, correct? So that's built into a standardized technology like Wi-Fi. Similarly, when your cell phone, connects, you power it up and it tries to connect to a network, it searches for a base station, base stations have base station IDs, etc., right? Your point is very well taken. But what I was saying is that it would require a standardization body to actually, so here, I did not use the fact that at all in anything I said, I did not use the fact that you could add station, sort of station identification radar IDs on top of, any of the waveforms that I'm sending. Certainly a possibility, but it would require, a standardization body for everybody to agree to do this, right? So I kind of hinted at this. This is quite, this topic is quite interesting because, it's people forget that radar needs to be treated. Radar consumes spectrum. That's the reason, we think it's a sensor, but it's transmitting, emitting, and receiving, so it consumes spectrum. So from that perspective, it is like a radio from a spectrum perspective, right? And for this multiple access problem, it needs some standardization, and that requires a body yet to be, which is yet to exist, and that body could do the kind of things that you're saying.
Right. I had one more question as well, and it was in regard to the angulature and the kind of structure of the kind of waves being emitted by these radars. And I was wondering if if those are polarized in certain planes, or if that's like how does the structure of these mission of the radar work?
Well, as I said, I think the most common radar waveform is these chirp waveforms. These chirp waveforms have been well studied, for 50 years, right? So these are linear chirps, and the reason they do this is, one is for the the power efficiency. Okay, so there are other reasons why these waveforms were chosen, right? And wideband where, they're, the power efficiency and the, remember, this waveform is a legacy from the radars that you see at the, say, the airport for air traffic control, okay? Or for, our, advanced radars used in, for the DoD. And there were other reasons why this technology matured. What we are seeing is because, from the hardware perspective, people know how to design the front end and then the digital baseband for it. It's sort of being, a low power version of it has been commoditized, right? If you are to, and there are, I believe there are a few startups which are, actually perhaps, more aligned with what you're thinking, that since these are low powered, remember, these are all mostly short range, these radars are expected for collision avoidance, to operate over, let's say, what, 10, 20 meters, maybe maximum 100 meters or so, right? So these could be all digital radars, in which case you could have a much richer suite of waveforms, right?
Thank you, Sumit, for a wonderful and very thought-provoking talk. It'd be interesting to see if any standards organization is going to look into that, and something we can discuss.
Oh, absolutely. I think this is one of the big missing things, I mean, a good parallel is, let me say this, DSRC or Wi-Fi, right? There's a, it's a radio which we all use. There was meant to be a radio like Wi-Fi or maybe LTE-V or CV2X, which is supposed to be put on vehicles, as John Barris said, right? But if you look at the vendors and the actual technology, there's not much evidence that the vehicle manufacturers actually want to integrate it or improve, standardize it, because it's not a traditional radio for use for traditional comms devices, right?
Thank you, Sumit. I think when you visit us in Maryland, we can have more discussion on that. So I'll give it back to Wale. Yeah.
Thank you so much, Professor, for that stimulating talk. As a token of appreciation, we have a plaque for you here. It reads Association for Computing Machinery, Baltimore Chapter. ACM Baltimore Chapter extends its appreciation to Professor Sumit Roy for delivering invited talk, ACM Baltimore Chapter 3rd Seminar 2023, Laurel, Maryland, April 27, 2023. Thank you so much again for your talk.
Thank you.
So this concludes our seminar for today, and I hope to see you next month.
Yeah, sure. I just like to give, that's fine, vote of thanks to all the committee members and also all the audience and folks. We're up there, listening to all the talks. There are a lot of things happening here. I know we look forward to other universities in Maryland, around Baltimore area, and Professor Barras is here. We had Anupam Joshi from Baltimore County. So we are planning to have a ACM conference or workshop as well in Baltimore. We're looking into that. So if you have any suggestions, please come in person and try to join our future seminars. And there is a Future Network World Forum. There's IEEE is taking place in Baltimore. Please try to come and attend that as well. That's happening in November. And there's a fast responder workshop that's going to take place at Hopkins Applied Physics Lab sometime in August. Also Open RAN Summit, that's happening the first week of August. So try to attend those as well. With that, I'd like to thank again and have a good evening and good day, good night. Thank you.